Hello friends, earlier we talked about the synchronous counters, up-down counters and the design of synchronous counters. In today's lecture, we shall be talking about the cascaded counters and the application of counters in general. Counters can be connected in cascade to achieve higher modulus operation. So, cascading means that the last stage output of one counter drives the input of the next counter. After completing this section, you should be able to determine the overall modulus of cascaded counters, analyze the timing diagram of a cascaded counter configuration, use cascaded counters to achieve specified truncated sequences, and finally use cascaded counters as frequency dividers. An example of two counters connected in cascade is shown in figure for a 2-bit and a 3-bit ripple counter. The timing diagram is also shown. Notice that the final output of the modulus 8 counter Q4 occurs once for every 32 input clock pulses. The overall modulus of the cascaded counters is 32, that is, they act as a divide by 32 counter. When operating synchronous counters in a cascaded configuration, it is necessary to use the count enable and the terminal count functions to achieve higher modulus operation. On some devices, the count enable is labeled simply count enable or some other designations such as G, and the terminal count is analogous to ripple clock output on some IC counters. The figure here shows two decade counters connected in cascade. The terminal count output of counter 1 is connected to the count enable input of counter 2. Counter 2 is inhibited by the low on its count enable input until counter 1 reaches its last or terminal state and its terminal count output goes high. The high now enables counter 2, so that when the first clock pulse after counter 1 reaches its terminal count, counter 2 goes from its initial state to its second state. Upon completion of the entire second cycle of counter 1, that is when counter 1 reaches terminal count the second time, counter 2 is again enabled and advances to its next state. This sequence continues. Since these are decade counters, counter 1 must go through 10 complete cycles before counter 2 completes its first cycle. In other words, for every 10 cycles of counter 1, counter 2 goes through one cycle. Thus, counter 2 will complete one cycle after 100 clock pulses. The overall modulus of these two cascaded counters is therefore 10 into 10 and is equal to 100. When viewed as a frequency divider, the circuit divides the input clock frequency by 100. Cascaded counters are often used to divide a high frequency clock signal to obtain highly accurate pulse frequencies. Cascaded counter configurations used for such purposes are sometimes called countdown chains. For example, as shown in the journal implementation of this countdown chain, suppose that you have a basic clock frequency of 1 megahertz and you wish to obtain 100 kilohertz, 10 kilohertz and 1 kilohertz. A series of cascaded decade counters can be used. If the 1 megahertz signal is divided by 10, the output is 100 kilohertz. then if the 100 kilohertz signal is divided by 10, the output is 10 kilohertz. Another division by 10 produces the 1 kilohertz frequency. Cascaded counters with truncated sequences. The preceding discussion has shown how to achieve an overall modulus, that is, the product of the individual moduli of all the cascaded counters. This can be considered full modulus cascading. Often an application requires an overall modulus that is less than that achieved by full modulus cascading, that is, a truncated sequence must be implemented with cascaded counters. To illustrate this method, we will use the cascaded counter configuration in this figure. This particular circuit uses 4 74HC 1614 bit synchronous binary counters. If these 4 counters were cascaded in a full modulus arrangement, the modulus would be 2 to the power 16 and is equal to 65,536. Let us assume that a certain application requires a divide by 40,000 counter, that is modulus 40,000. The difference between 65,536 and 40,000 is 25,536, which is the number of states that must be deleted from the full modulus sequence. This technique used in the circuit of figure is to preset the cascaded counter to 25,536 each time it recycles, so that it will count from 25,536 up to 65,535 on each full cycle. Therefore, each full cycle of the counter consists of 40,000 states. Notice in figure that the RCO output of the rightmost counter is inverted and applied to the load input of each 4-bit counter. Each time the count reaches its terminal value of 65,535, RCO goes high and causes the number on the parallel data inputs to be synchronously loaded into the counter with the clock pulse. Thus, there is one RCO pulse from the rightmost 4-bit counter for every 40,000 clock pulses. With this technique, any modulus can be achieved by synchronous loading of the counter to the appropriate initial state on each cycle. Counter decoding. In many applications, it is necessary that some or all of the counter states be decoded. The decoding of a counter involves using decoders or logic gates to determine when the counter is in a certain binary state in its sequence. For instance, the terminal count function previously discussed is a single decoded state in the counter sequence. Suppose that you wish to decode binary state 6, that is 110 of a 3-bit binary counter, when Q2 is equal to 1, Q1 is equal to 1 and Q0 is equal to 0. A high appears on the output of the decoding gate, indicating that the counter is a state 6. This can be done as shown and is called active high decoding. Replacing the AND gate with a NAND gate provides active low decoding. Decoding glitches. The problem of glitches produced by the decoding process was discussed in earlier lectures. As you learned, the propagation delays due to the ripple effect in asynchronous counters create transitional states in which the counter outputs are changing at slightly different times. These transitional states produce undesired voltage spikes of short duration called glitches on the output of a decoder connected to the counter. The glitch problem can also occur to some degree with synchronous counters because the propagation delays from the clock to the Q outputs of each flip flop in a counter can vary slightly. Figure shows a basic synchronous BCD decade counter connected to a BCD to decimal decoder. To see what happens in this case, let's look at the timing diagram in which the propagation delays are taken into account as shown in figure. Notice that these delays can cause false states of short duration. The value of the false binary state at each critical transition is indicated on the diagram. The resulting glitches can be seen on the decoder outputs. One way to eliminate the glitches is to enable the decoded outputs at a time after the glitches have had time to disappear. This method is known as strobing and can be accomplished in the case of an active high clock by using the low level of the clock to enable the decoder as shown in this figure. The resulting improved timing diagram is shown here. Counter applications, digital clock. A common example of a counter application is in the timekeeping systems. The figure here is a simplified logic diagram of a digital clock that displays seconds, minutes and hours. First, a 60 Hz sinusoidal AC voltage is converted to a 60 Hz pulse waveform and divided down to a 1 Hz pulse waveform by a divide by 60 counter formed by a divide by 10 counter followed by a divide by 6 counter. Both the seconds and the minutes count are also produced by the divide by 60 counters, the details of which are shown in this figure. These counters count from 0 to 59 and then recycle to 0. Synchronous decade counters are used in this particular implementation. Notice that the divide by 6 portion is formed with a decade counter with a truncated sequence achieved by using the decoder count 6 to asynchronously clear the counter. The terminal count 59 is also decoded to enable the next counter in the chain. The hours counter is implemented with the decade counter and a flip flop as shown in this figure. Consider that initially both the decade counter and the flip flop are reset and the decode 12 gate and decode 9 gate outputs are high. The decade counter advances through all of its states from 0 to 9 and on the clock pulse that recycles it from 9 back to 0, the flip flop goes to set state, that is j is equal to 1 and k is equal to 0. This illuminates a 1 on the tens of hours display. The total count is now 10. The decade counter is in the 0 state and the flip flop is set. Next, the total count advances to 11 and then to 12. In state 12, the Q2 output of the decade counter is high. The flip flop is still set and thus the decode 12 gate output is low. This activates the PE bar input of the decade counter. On the next clock pulse, the decade counter is preset by state 1 by the data inputs and the flip flop is reset, that is j is equal to 0 and k is equal to 1. As you can see, this logic always causes the counter to recycle from 12 back to 1 rather than back to 0. Automobile parking control. This counter example illustrates the use of an up-down counter to solve an everyday problem. The problem is to devise a means of monitoring available spaces in a 100 space parking garage and provide for an indication of a full condition by illuminating a display sign and lowering a gate bar at the entrance. A system that solves this problem firstly consists of optoelectronic sensors at the entrance and exit of the garage. Secondly, it provides an up-down counter and associated circuitry, and finally, it gives an interface circuit that uses the counter output to turn the full sign on or off as required and lower or raise the gate bar at the entrance. A logic diagram of the up-down counter is shown in this figure. It consists of two cascaded 74HC190 up-down decade counters. The counter is initially preset to 0 using the parallel data inputs. Each automobile entering the garage breaks a light beam, activating a sensor that produces an electrical pulse. This positive pulse sets the SR latch on its leading edge. The low on the Q bar output of the latch puts the counter in the up mode. Also, the sensor pulse goes through the NOR gate and clocks the counter on the low to high transition of its trailing edge. Each time an automobile enters the garage, the counter is advanced by 1, that is incremented. When the 100th automobile enters, the counter goes to its last state. The maximum minimum output goes high and activates the interface circuit, which lights the full sign and lowers the gate bar to prevent further entry. When an automobile exits, an optoelectronic sensor produces a positive pulse, which resets the SR latch and puts the counter in the down mode. The trailing edge of the clock decreases by count 1, that is decremented. If the garage is full and automobile leaves, the maximum minimum output of the counter goes low, turning off the full sign and raising the gate. Parallel to serial data conversion. A simplified example of data transmission using multiplexing and demultiplexing techniques was introduced in earlier lectures. Essentially, the parallel data bits on the multiplexer inputs are converted to serial data bits on the single transmission line. A group of bits appearing simultaneously on parallel lines is called parallel data. A group of bits appearing on a single line in a time sequence is called serial data. Parallel to serial conversion is normally accomplished by the use of computer to provide a binary sequence for the data select inputs of a data selector oblique multiplexer as illustrated in this figure. The Q outputs of the modulus 8 counter are connected to the data select inputs of 8-bit multiplexer. The timing diagram here illustrates the operation of this circuit. The first byte, that is 8-bit group of parallel data, is applied to the multiplexer inputs. As the counter goes through a binary sequence from 0 to 7, each bit beginning with D0 is sequentially selected and passed through the multiplexer to the output line. After 8 clock pulses, the data byte has been converted to a serial format and sent out on the transmission line. When the counter recycles back to 0, the next byte is applied to the data inputs and is sequentially converted to serial form as the counter cycles through its 8 states. This process continues repeatedly as each parallel byte is converted to a serial byte. So friends, that brings us to the end of our discussion in this lecture, and therefore we sum up. The maximum modulus of a counter is the maximum number of possible states and is a function of the number of stages. The maximum modulus is equal to 2 to the power n, where n is the number of stages in the counter. The modulus of a counter is the actual number of states in its sequence and can be equal to or less than the maximum modulus. The overall modulus of cascaded counters is equal to the product of the moduli of individual counters. So, that is it for today. See you in the next lecture with more on digital circuits. Thank you very much.